Kubernetes. And we're actually, oddly enough, the largest privately held contributor to the CNCF right now, which is kind of cool. You know, we found this out by accident. Somebody else pointed it out. But what we do is we develop code to make stateful applications work in Kubernetes, and then we open source it, and we build some commercial management software on top of that to make it a little easier for people to use. But it's fully 100% usable as open source, and this presentation is all 100% open source. There's no commercial software in this at all, not even on the laptop. So we're going to start at the very beginning. Who can tell me a little bit about cloud-native software and Kubernetes? Who's familiar with cloud-native software design patterns? All right, so we've got a few people that are familiar with cloud-native design patterns. How about Kubernetes? Who's got kube control on their machine? Come on, there must be more kube control out there. All right, we've got maybe, 10, 15% of the room? Okay, well, cloud-native software is software that's designed as typically microservices, little components that communicate with each other, that have a single role, and a role that they do well, and well-defined interfaces into other components. The idea being that you create a system where the individual components are not tightly coupled to each other, so that the engineers who have to work on that component don't have to spend all day communicating with other engineers working on adjacent components. So as a design philosophy, it works great. The industry has moved there, and the industry is choosing Kubernetes as its deployment mechanism. I mean, there were a lot of other deployment mechanisms out there. Apache Mesos was a really good one. There's some advantages that Kubernetes has that are, I think, really important, though. And the first advantage for me is that it's an open source infrastructure abstraction. You can define all of your application's requirements in a YAML-based DSL that tells the infrastructure orchestration software where to put your application. The other important thing about it is that it's declarative in its configuration. So the configuration that you write is in a configuration like you would write a shell script, where it says run this command, then run this command, or Ansible, or there's a lot of other frameworks that work like that. Declarative systems describe the end state of the system. And so it's just a description of what the infrastructure is supposed to look like. And then the rest of the software looks at what the state of the machines actually is, compares that to what the state of the machines that it's expecting it to be, and makes little changes to get it closer to the desired state. And so that's an important part of how Kubernetes works. And it's a little backwards sometimes. You'll create an application and then create a bunch of stuff, and then you'll make some storage for it, and then all of a sudden everything just snaps into place and starts up. You don't have to do everything in order. So the reconciliation loop is the software that handles that comparison to the state of the world, and pushes these actors into getting the state of the infrastructure to the desired state. So this is a laundry list of Kubernetes concepts. And I'm just going to kind of go through them one by one. And if I'm going too slow, please let me know. So in Kubernetes, things that you run Kubernetes on are nodes. That's the host, and it could be a virtual machine or it could be a bare metal machine. But the nodes are all kept track of, and you can list them out by name. And I'll sprinkle in some command line with this. And is that readable to people in the back of the room? A little, okay, good. So let's see, CTL get nodes. Let's see what we see. Well, we see a bunch of nodes. This is my test cluster. And the nodes are all listed out by name. Kubernetes itself has a notion of the status of each node. So if one of them is turned off, it knows that. And it has a notion of the roles and what this particular machine is for. The different types of nodes that I have in this collection are master nodes, worker nodes, and these storage nodes, which are specialized worker nodes that have disks attached to them. But the master nodes are where the Kubernetes brains are. That's where the scheduling software runs that knows about what's going on all the worker nodes. And we have 3 of them for reliability. If any of them go offline, there's still 2 masters that know the state of the world. So another sort of core concept for Kubernetes is labels. Like everything gets these labels, and the more familiar you are with the labels, the easier it is to manage large clusters, I think. But you use them to select things instead of specific host names, for example. You just label that host with an app identifier, and then you can place an app based on a label instead of based on the host name. And that way, if the host name changes, you can move the label, the app moves with the label, it's all good. So that's a core concept for Kubernetes.
Quick question.
Sure.
Are your master nodes running etcd?
Yes. Yeah. And that is an excellent question. etcd, who knows about etcd? Do you want to share with the room what etcd does and what it's all about in a Kubernetes context?
I guess it stores the state of Kubernetes, and it really sucks when it breaks.
Oh yes, it's a key value store, and not an awesome one. It's a pretty good one, and it's got pretty good scalability and pretty good performance. And so most people use that for keeping all the state in their Kubernetes clusters. And so you have these 3 etcd instances, and they typically run on the master nodes. And these will synchronize state with each other so that there's always a consistent view of the world. You can replace etcd with other things, and that's a really core thing for Kubernetes, is that everything is pluggable. It's an open source project, and everything has been built with a view towards modularity and loosely coupled systems. Consequently, you have situations where people can't scale etcd big enough, and then they'll use some different thing. They can modify etcd to scale better. In practice, I find it easier to use small clusters and multiple clusters rather than trying to run all of the things in a single cluster. But there's a lot of difference out there. So people have apps that are that large that they need to run it in a single Kubernetes cluster just so that everything integrates. And then you need to pay special attention to how your key value store is scaling. Any other questions about nodes, labels, master nodes, that sort of thing? Yes?
How much can etcd scale? Like, I've heard that it breaks after, X number of nodes.
I don't know. But I suspect that it has to do with the number of objects you have in your cluster. And so you could have a huge cluster with 2,000 machines, where every machine is running 1 or 2 apps. and etcd runs fine. Or you can have, you know, a suite of microservices that spins up a new instance of itself every time somebody connects to it, and run out of scalability really fast in a small cluster. That's a guess, though.
I'm having a CD cluster with like 6 nodes, and like, for some reason it got corrupted and like just completely killed the cluster. I was trying to figure out, has that improved nowadays?
It's really quite stable now. Kubernetes itself is in version 1.17, and you know, it's an open source project. So how many of us work with open source software every day? That's like everybody in the room. And so you know that the open source projects have a life cycle, and you know, early on they can hurt. You know, I mean, you can really run into some glaring issues with it. But now is no longer early on. It's matured in the last couple of years to be a pretty reliable piece of infrastructure that a lot of people use in production right now.
Also, the 6 nodes, that would be you need an odd number of nodes for an etcd cluster so that there can be a quorum in case of a network partition.
Like 6 plus 1.
What was that?
6 plus 1.
Okay, so 7.
Yeah. So I don't know. I run my clusters with 3 master nodes and with etcd running on them, and they work pretty darn well for my purposes. And so, what do you put in etcd? Well, you put in all the information about these objects that Kubernetes knows about. One of the basic things, I mean, what Kubernetes does fundamentally is it puts containerized applications somewhere on some server that's running Docker or Containerd. And so it's all about putting containers down. And these pods are a collection of containers, and they're sort of the primitive for Kubernetes. You know, your application goes in a pod. That pod might have multiple containers. Common reasons to have multiple containers are to, you know, query shared memory. You know, you in situations where you need to group 2 applications on the same node so that they can communicate directly with each other, that's when you put multiple containers in a pod. But for the most part, you can think of a pod as an application container. And so you might have Postgres running in a pod, or Nginx running in a pod. Deployments and stateful sets collect up pods. And what they do, let's take a look, because I think this will be better as an illustration. If I do get pods, I'm going to try and shrink this down a little bit so that that's, can you still see that in the back? So, yeah, when we get the list of pods, we see this MinIO instance. What's MinIO? It's an SD compatible object store. You can run it as an application in Kubernetes. I use it all the time because I do storage in Kubernetes, and so it's really easy to transfer files back and forth to your Kubernetes cluster with MinIO. But it's a good sort of sacrificial application for a demo. You know, we have this MinIO instance up and running. But if we look at the deployment that's associated with this, there's a couple of things that I'll point out. You know, the deployment gets the real name, and this pod gets this randomized suffix. The pod is, you know, the pods are cattle, and there's no reason to keep any given pod around for any given length of time or give it a real name or anything like that, because they come and go all the time, especially in stateless applications. You know, you'll automatically scale up, and those scaling characteristics are influenced by the deployment. So if we do a describe deployment, and look for stretched. You can see that it has all the information that you need to run this container and all the information it needs to expose the container and actually deploy the application. But it also has information about how many replicas you want it to have. So in this case, we have one desired replica, and it knows that it's available based on health checks that are configurable. Let's see, how else can I describe deployments? If we take a look at GitLab, there's a few different kinds of deployments in there. And you'll see, for example, this registry server has 2 desired containers and 2 that are ready, 2 that are up to date. You can see the age that the deployment has been around and compare that to the age that the pod has been around. Lots of observability built into the system. Now, stateful sets, well, first off, the difference between deployments and stateful sets is that with deployments, you don't really care where they go. You just want 100 instances of this application. With stateful sets, there's a reason that you want it to be on this particular node. And that reason is almost always storage. And so stateful sets are, were introduced, I think, it hasn't been more than a year or two, but they were introduced to support stateful applications in Kubernetes and to support the ability to, make sure that this application pod keeps landing on the same box so that it's got access to the same storage. Any questions about deployments and stateful sets?
Don't deployments do the same thing as stateful sets nowadays?
You can use node selectors with deployments, but they often get used for different things. So I'm not sure what the source of the question is. I mean, there may be enough feature creep that they're like kind of able to be used in the same situations, but they're fundamentally 4 different things. Yeah, like if you take a look at the Helm charts for stateful applications, they typically will use a stateful set when they deploy rather than a deployment, and it's to enforce that connection to the storage.
What happens if a node that a stateful set, like a pod from the stateful set is deployed on, goes down? Does that pod then not automatically get started on?
It won't get restarted on a different node. I'm pretty sure of that. I mean, we could try it if you want, but it's stuck to that node because of the, again, typically because of the storage.
So if you have an empty dir volume on that node that pod is using for a stateful set, once that node comes back online, presumably the stateful set the pod will spin back up and the stateful will be able to use that same empty dir volume.
Yeah, that's the expected behavior. What you find, like, just as an example, we deploy in OpenEBS our CStore replica pods as a stateful set. Now, CStore is a type of storage engine that you can use with OpenEBS. It has ZFS implemented in it, so you can aggregate disks with it and carve out volumes with it. And so you can use it to service PDC requests for arbitrary applications, and the application pod communicates with the storage over iSCSI so they can be decoupled. That's the 10,000-foot view of CStore. But to come back to the question, that technology uses a stateful set to make sure that the ZFS pod comes back up on the node that the disks that it's aggregating were attached to. And when I take down a node that has an OpenEBS stateful set sitting on it, that pod goes away. But what you find commonly with stateful sets is that they get used for applications that, like CStore, handle their own replication. So if you're using MongoDB, for example, and you have a MongoDB cluster, then maybe it has 3 nodes, but maybe it's in an auto-scaling group, and you have things set up so that they come up on a new node and they get a local directory there to store their state in. But then that instance of that database has to keep coming up on that same node, and so that's where stateful sets come in handy, I guess, if that makes sense. And then when the node is down, that particular instance of MongoDB isn't syncing data anymore because the application is running. And when it comes back up, it's going to have to query its peers, and it's going to have to sync over all the data that it's missed while it was rebooting or while it was offline. So that gets handled in the application layer in something like MongoDB, and also in CStore. And you'll find a lot of applications that have that behavior use stateful sets so that they can, keep whatever left, like whatever incomplete data set they have, and not have to fill the whole thing in. Any other questions? Deployments and stateful sets. Cool. Services. So not much use to all this code without being able to talk to it. And so services define how you connect to your application. And if you just take a look at one, it'll make perfect sense, I think. This is the application that we're messing with. It's sitting on a load balancer. Its external IP is this. It's on port 9000. We can telnet to it and make sure that it's there, because we love telnet.
Is your Kubernetes cluster in a public cloud?
Yes.
Okay. So the load balancer.
Yeah. It's in 2 public clouds.
Okay.
This one is in Packet and DigitalOcean. But that's how you expose these services. And this ends up talking to the MinIO application, based on the configuration of the service and the configuration of the application. Again, taking advantage of labels to make sure that everything gets stitched together without any, specific references to this specific application pod. So those are services. Now volumes and PVCs. So when you do want storage, what you do is you create what's called a PVC, or a persistent volume claim. And so if I look at the PVC associated with this app, the status says bound. Now that means that there's a PV that's associated with this PVC. In my case, it's a CStore PV, but it could be a traditional local PV in Kubernetes, or any volume backing it that Kubernetes supports. An EBS volume in AWS, EKS, or anything. So that's the PVC. Now, if you look at the PV, in this case, I'm going to have to grep it out here because this output is going to be kind of long. But you can see, the volume is the same size as the claim. This is an indication of how many pods can access it at a time. Like, that you can, if you're using NFS, you can have multiple pods accessing it at a time. This PBC label here is the name of the volume, which you can track to a particular location on disk in a store pool, but it could be any type of volume. So the volumes get associated with the application like this. Get PVC backup, describe. So you can see that this is mounted by that pod really easily from this. And, and this observability is automatic. It just tells you that. Let's see.
Is a C-store only like block storage that supports read-write once type access, or is there a capability to do more like an NFS or file system type storage that supports read-write many?
Well, we're kicking around what the right way to do read-write many is right now. The problem is the file system. You need good locking in your file system, and NFS figured that out a long time ago, and nobody seems to want to rewrite that. I mean, we want to do a high performance read-write many in our new storage engine, but it's tricky. I mean, ext4 doesn't support that kind of use case. Neither does XFS. There are file systems that do. Which one do we pick? Open to suggestions if anybody has a favorite clustered file system, but we're trying to figure it out ourselves.
Could you do something like, so you're already using ZFS under the hood, dynamically provision a ZFS data set and then just serve that up via NFS?
We have a blog post actually that goes through using the standard NFS provisioner to expose a C-store volume, that you mount in this NFS pod, and then create a storage class out of that. And it's pretty cool. I mean, this is one of the great things about Kubernetes is that it's so extensible that you can literally take a cluster, make some disk on it, and then modify the cluster so that you can feed stuff through an NFS that references that same cluster and mounts the storage and exposes it only to the applications in that cluster. So you can have NFS mounted home directories for your pods if you want. But that's a little different than this than the storage class supporting read-write many natively, and we want to do that too. But it's not ready yet. So that's volumes. Namespaces are important. If you do kube control get NS, you can see I have a bunch of different namespaces on them. All these objects, most of all of the Kubernetes objects, most of them have a namespace associated with them. And pods have namespaces, services have namespaces. The important takeaway from namespaces is that they're not just easy to organize. It's not just easier to organize things. You want to design your app so that it expects everything to kind of be in that namespace, right? Or to be in a different namespace for maybe some specific reason, right? Like you'll see, just as an example of my usage of different namespaces, OpenEBS installs in its own dedicated namespace. And so you can see the pods there, you can see the deployments there, you can see the services there, and all these different types of objects are, sort of interrelated, and that's why you collect them in one namespace, right? And then when you are sitting on one of those pods, you don't have to use complex DNS names to get to the pod in a different namespace. Config maps and secrets are another namespaced object that you use kind of like you use persistent storage, but it's specifically for mapping a configuration file or maybe a like an SSL certificate or something like that. And config maps are just stored in clear text. You can edit them. They have some metadata associated with them. But then one of those pieces of metadata is where you want the configuration file to show up. And so you can use that to configure your applications. And then these secrets put some, basic obfuscation around it so that you're not looking at a clear text password. But when you start getting into the role-based access control, different roles will be able to see the secrets and and other roles will not. You want your application to be able to see the secret, but you may not want your app administrators to be able to see the secret, for example. Now, CRDs. kubectl gets CRD. There's a lot of them in here. And what they are and what it stands for is custom resource definition. They are the things that you look at with kube control. Objects like pods. If we just take a look at the OpenEBS ones. Oops. You can see all the different types of accessible objects in here. Block devices, block device claims, CStore backups, CStore pool instances, and all that. And this is important because Kubernetes is extensible in such a way that you can create these new objects. And so, different pieces of software that you add into your Kubernetes cluster will populate Kubernetes with new types of objects. One type of object you might not be familiar with is a block device. So you can say kube control get BD if you have OpenEBS installed, and it'll tell you, okay, so on this machine you have this block device named this, and it's got this much storage on it, and it hasn't been claimed by any storage that's configured.
The block device is a custom resource defined by
OpenEBS. Yep. Yeah, and we run a little daemon set that goes and discovers the disks and populates etcd, and then we wrote some CRDs that allow you to look at them and retrieve them from etcd.
Like disks as in direct attached storage on each node?
Yep. Yeah, like if we describe one of these, just real quick, and I'll come back to you in just a second.
So in other words, it's kind of like Rook and Ceph, sort of?
It's very similar to Rook,
Okay.
except for the fact that the storage is implemented in containers. Okay? Now with Rook, what you have is an orchestration layer on top of an external Ceph cluster, which is cool if you like Ceph and you have a Ceph cluster. But if you don't have Ceph, you might want to do your storage inside of Kubernetes. And that way, all of your Kubernetes expertise is leverageable, and all of your, the work that you do to secure your clusters is the same for securing your storage. So there are a lot of advantages to our architecture, in my humble opinion, as a guy who works at the company that writes the software, right? You'll evaluate and make your own decisions as you find out what your use cases are and what your real needs are. But one of the big differences is that Ceph gives you a big pool of storage. Like you get 60,000 IOPS out of a Ceph cluster, and like you carve that up however you want. And what we do is we give you these block devices. And so it's a little bit more like with AWS EBS devices, where like you get this device, it's sitting on these disks, and it has these performance characteristics. And the stuff sitting next to it doesn't impact the performance characteristics. So it's just a different architecture. Yes, question.
What do these objects hold? What data do these objects hold?
The objects hold, the block device objects hold a lot of information
Is it
about the
related
block
to the
device.
disks that the cluster is attached to, something like that? Or?
Yeah, like this is a describe on the block device. And so you can see a bunch of sort of metadata information from Kubernetes, but I'll point out some good stuff. Like this is the model string and serial number from the hard disk. You know, from the smart info in the kernel or wherever it gets it. I don't even know where it gets it from. You know, these are the WWNs if you have a SAN environment. You know, I mean, that's useful to have. This is the, you know, the device node path. So you can identify, you know, this specific hard disk is in my Kubernetes cluster using these CRDs. And then you can group them together and make big pools of disk like I have. I'll show off this cluster a little bit more. And, you know, 20 terabytes on this box, another 20 terabytes on this box, another 20 T on this box, and they're all associated with this one pool of storage. So if I look at that pool of storage, you know, this is a list of storage classes, and this is the storage classes associated with those disks. And then, like, if we want to say, back up, and then, oh, am I going to remember what that CRD is? It's a there we go, and CR. Cool. Uh-oh, one of our nodes is, or volumes is degraded, which is not surprising because we've been abusing that storage class. But yeah, let's see. If I go back to this PVC and I grep this volume name out of this list, I think that'll give us a more manageable thing to look at. Yeah. All right. So this is the min.io volume that we're working with. And you know, we can just see from this command that it's got 3 healthy replicas, and each of these replicas is sitting on a different machine. 2 of them in Packet and 1 of them in DigitalOcean. And so every block write that goes to this block device is persisted across 2 clouds. And controllers and operators. How do we do all this stuff? Creating these custom resource definitions, everything like that. Well, you do it with operators, which are a special kind of controller that creates custom resource definitions. So that was a lot. There must be some questions. Any feedback on how fast or slow I'm going? Yeah.
So let's say you have like EBS and AWS.
Uh-huh.
You're breaking that off into multiple block volumes
Mm-hmm.
and creating like persistent volumes out of that.
Yep.
So that was the whole point of it.
Yeah, that's the whole point. If you
And then you
have an
create,
EKS
like,
cluster,
persistent module claims and like use these PVCs.
Yep.
Sorry, PVCs.
yeah, you might have an EKS cluster and then create a like a 3 or 4 node group that's like a, you know, I think I3 or something like that is a good storage node, an IO optimized node that gets good throughput and probably, I think, has NVMe in most regions. And then you can just take that, you can create C-store pools across them, and you can use that local storage to serve persistent disks. And then if one of the nodes goes away, well, that collection of storage is gone, but you still have two replicas, and you can spin up a new node, and you can fill a third replica in so that you can get back to your stable 3 replica state. And that backfilling happens automatically. So yeah, you can use cloud devices, but you can also use, these packet systems are bare metal, and so it discovers any block device.
But if you're in a public cloud, like, what's the benefit of using this architecture as opposed to creating new EBS volumes for all of your things?
Yeah, that's an excellent question. One of the use cases that we see a lot of is multi-zone replication. AWS won't do that for you. So people use OpenEBS to do that. The other thing that people use it for, there's 3 different types of storage engines, right? So CStore is good for stuff that you need replicated. But there's also an OpenEBS local PV. And local PV host path, you can just mount a disk on your nodes at the same place every time. Like if you're in AWS, they'll even format it and expose it for you. And then you can just land, ephemeral pods or ephemeral disk on that piece of file system there. So a lot of people use OpenEBS for dynamically provisioning local PV volumes as well, just because it's easy. There's no manual intervention. So in an application that has 5 or 6 volumes, you don't want to have to manage that by hand. So, and if it has 30 or 40, forget about it, right? So we've covered a lot of the concepts on this slide, but not the components. So we talked a little bit about etcd. The API server is sort of the central clearinghouse for everything. The scheduler is responsible for picking a node to stick the application on, and it knows how much memory is in use on all the nodes and everything like that, so that it can make a good decision. The kubelets. Kubelet is a process that runs on the worker nodes. It runs on all the nodes, and it's kind of the acting agent for anything that Kubernetes wants to get done on a particular node. So if you need to start a container on a node, Kubelet handles that. And if you need to attach storage to that pod, then Kubelet handles that too. And so this is sort of like a bird's eye view of everything component-wise, and they all talk to each other over, just regular old IP addresses and services that are implemented in Kubernetes. So we talked about extensibility, and we talked about what operators are. I dropped a nice discussion from Stack Overflow in here about, really what's an operator, what's a controller. Well, Litmus is an operator, and it creates some of these custom resource definitions to do very specific things to your applications in Kubernetes. And it's an operator, and it follows the controller pattern, and etc. So, all right, we said that kubelet is responsible for starting the pod, but there's more to it than that. This is the best description of the actual workflow I've come across, and so that's why I put it up here. Are there any questions about this? Does that make sense to everybody? So it comes, your user does an API call that writes to etcd, and then when the scheduler wakes up, it sees this stuff in etcd, and it writes more stuff to etcd about where the pod should be. And then kubelet wakes up, and it goes and asks etcd, well, what's supposed to be on here? And then tells Docker to go run the app, which then tells kubelet to tell etcd that the app is running. So it's all sort of like, driven by the component that's closest to the hardware. And it gives you this sort of composable infrastructure that kind of comes together as you watch, which is pretty fun. So everything is stateless. What am I talking about? I mean, we've been talking about stateful applications and storage this whole time. Well, Kubernetes was designed originally for stateless applications, and it was written by Google. And Google's response for a while to what he's supposed to do with application state was, well, store it in your cloud provider's database service, which is an awesome idea if you're a cloud provider and in the business of making money off of your database service. It turns out that most people have, like, the bulk of their spend is for storage. The bulk of their cloud spend is for storage. Some it's half and half, some it's really heavy weighted on storage. So if you can find ways to use the storage more efficiently, you can shave some dollars off. And you can make it easier to move out of that cloud. If you wrote your whole application with Google's database in mind, trying to get that application to Azure is going to be hard. So what do you do with the application state? Well, you store it in Kubernetes, and we talked a lot about OpenEBS and dynamic provisioning. It's 100% open source. It's a CNCF project. You can install it in about 2 minutes on your Kubernetes cluster, and you have running storage. So, it has a really active community, and I'll invite you all to jump on the OpenEBS Slack group and say hello. If you're tinkering with it, if you have any questions about it, jump on. Everybody's super helpful. So what about Litmus? I mean, this talk is about Litmus, right? So when you have state in this dynamic, ever-changing infrastructure where pods are coming up and going away all the time, you're going to run into scenarios where some application component can't get to its state for some amount of time. Well, that's kind of the problem with cloud-native application design, is that you trade, the maintainability for a little bit of extra work on interfaces, right? The nice thing about using Kubernetes is it gives you a consistent way to orchestrate all that. But what Litmus takes advantage of is the fact that it's all now machine controllable. All your infrastructure, since it's completely abstracted, you can manipulate with code. So that's what Litmus does, is it manipulates your infrastructure to test the software that's running on Kubernetes. So common test strategies, you take all the unit tests, you do some integration tests, you kind of glue all that together, you deploy it in staging and do some scaling testing, and then you ship it, right? Well, if you do that way, you are bound to miss something that happens when you change your infrastructure, right? And so if you can take those tests, that scaling test, that battery of unit tests, and run them while you're injecting chaos into the environment, then your CI/CD pipeline becomes like the worst production environment you've ever run in. And so that lets you find weaknesses that you never would have thought of. It lets you fix them before it hits production. And then eventually it lets you run your chaos testing in prod so that you're specifically forcing the faults. There's a lot of different ways that you can do that. Kubernetes makes it really easy to do A/B testing, canary testing, and all kinds of stuff. And so there's plenty to read up on that. So that's what Litmus does, is it's cloud-native chaos testing, right? So it manipulates pods, PVCs, network connections, and it does it with some new CRDs that work the same way as everything else does in Kubernetes. So, you add an operator that installs some CRDs, you inject your chaos by creating a chaos engine, um, and and we collect all these different types of experiments in Chaos Hub, which is sort of a repository, like kind of like Helm is for anybody who wants to upload a chaos test. We have generic chaos tests up there. We have some chaos tests for Kafka, and Litmus is 1.0, and so it's ready to be added to and extended, but we're just building up the community around it now. So I would encourage everybody to like if you do develop a cool test, share it with us, and then all of your fellow testers will have access to that. We're working on gaining GitHub stars, so star us if you check us out. And there's another thing. I'll put in a plug for this. This is an OpenEBS specific plug, but we're a CNCF project, and the way you percolate through the CNCF organization, one of the ways is to get people to sign your adopters file. And so if you're using OpenEBS for something cool in production, sign the adopters file. Tell us what you're doing with it. It helps us work with the CNCF and get more resources. And if you want to check back for the freshest features, check back on the 15th or the 16th of the month. We release every 15th, and it's the same cadence that OpenEBS is on. So it makes it really easy. We usually do a webinar at the beginning of the month and talk about the latest features, and that's really it. We've been doing some interactive. Does anybody want to see some more of anything in particular?
Yeah, actually.
Yeah? Mm-hmm.
So you've got this cloud.
Mm-hmm.
Can you point Litmus at it and make it mess with your cloud?
Absolutely. So, let's take a peek at this app that we have. It's in here somewhere. Oh, I guess I can just... back up. And so, I have some files on there. I'll upload chaos.yaml. Why not? Upload it successfully. Terrific. We can upload 500 bytes. This is probably going to be a better test for interrupting things. So, MinIO is an object store. It's writing this file to, the 3 replicas in that CStore volume. And what I'm going to do is I'm going to clobber that MinIO. So if I do control get pod backup, we can see that's running. Delete -f chaos. And let's take a look at this chaos.yaml. So this is a chaos engine. It's a namespace object, and it helps everything work better if you put it in the same namespace as your application. And you will also want to put the chaos engines in that same namespace when you pull them from Chaos Hub. Okay? And then you specify the application that you're targeting, the namespace of the application, the label of the application, and that it's a deployment. You do have to create a service account so that Litmus is allowed to manipulate the pods in that namespace. And so this is a reference to that service account. I have an example right here, but this is just straight off of our website, so there's not much to look at there. And you can see the experiment name, the pod delete, and the value of the container name. Let's control live, and let's see if it works. So now you remember there was only this min.io stretched pod in there before, right? And so this is running this pod delete job now. And you can specify a lot of options around the frequency and delays in between events, and build these things up. But now you can see that the delete pod is running. And in a few seconds it'll delete that min.io, or it's supposed to delete the min.io. Oops. What's going on with our min.io? Oh, it's down. So it's going to create a new container and it's going to attach to the storage, and it'll come back up. Not an exciting use case, but hopefully an illustrative one, right? And then you can get the let's see, chaos result. Donk. Perfect. It's still waiting. Let's see if it comes back up. Well, it's running. Not ready yet.
It's not ready yet.
Come on, readiness check. So, yeah, that actually brings up, by the way, one of the cooler things about Kubernetes is that it's a very common pattern to build these checks into your deployments that know when the pod comes up and when the pod starts serving requests, and you have a common way to look at that across all your applications, which is pretty powerful. It's sort of built-in monitoring. And there's the app again. So that's how Litmus works.
Thank you.
You're welcome.
You say run this in production and break stuff. Now, I don't know if it's typical for something to take this long to come back to life. But if I do this in production, I'm going to get a lot of angry customers.
Oh yeah. Yeah, and this is one application that has a single instance. Your application probably has multiple components and sits behind a load balancer, maybe?
Yes.
Yeah. So what's interesting for you to find out is what happens when you kill one of those instances when the system is under load, or what happens when you kill off 10 of those instances when the system is under load. And how fast does it spin up new replicas and that sort of thing. But this is really just the simplest, most illustrative example that I could think of. If you want, we can write a little chaos experiment and see how something like GitLab deals with G-unicorn dying. And then we'll know how GitLab behaves when you break G-unicorn. But I would be going shoot from the hip on that one.
Break stuff in production.
Oh well, I'm a developer advocate. I don't have any production. So, further questions? Yes.
How does this differ from something like chaos monkeys and something like that?
Well, this is purpose built for Kubernetes and with Kubernetes in mind, but it's very much inspired by Chaos Monkey. And there are other projects. There's one called something Seal that Bloomberg developed. They're really hot on Kubernetes and they're OpenEBS users too, and they're merging their project in with Litmus. So Litmus is kind of becoming the centralized clearinghouse for chaos testing in a Kubernetes environment. But like any open source project, it's only as good as the next project that comes along and does it better. So we're racing to extend it and keep it going well. Yes.
So does Litmus only kill Kubernetes? Is it like the site was down, right? Does it record? Oh, it took the node 10 minutes to come up, or anything like that?
Well, Kubernetes itself is very observable, and so that information is there. Let me see if the chaos result. So what we got is a pass as a status, that's all we get. But this is just manipulating the infrastructure. Like any software testing enterprise, you're really looking for the logs in your own product that are telling you how the application is behaving based on the infrastructure changes. And so in this case, we have a verdict of pass because Kubernetes did what Kubernetes is supposed to do. Whether your application did what your application is supposed to do is a different question. If it's supposed to spin up another pod and replicate data to it, then that's a little out of scope for Litmus. But if you wanted to inject network latency while it's refilling, then that's definitely in scope. Other questions? No? Anything you want to see? Yeah.
What can you do with like this? Like, what errors can you mock out?
So we can kill a container inside a pod. We can simulate disk full, disk loss. We can hog the CPU on that node that the application is running on so that the app gets CPU starved. These are the kinds of things that you can do. And it's under active development. So if you think of anything else that you want to manipulate, then let us know. And this is just the generic one. There's some Kafka specific ones on Chaos Hub too, if you want to check those out. Mm-hmm.
What is node drain?
When you are gonna put, like, if you're familiar with maintenance mode in ESXLAN, it's the same sort of thing where, like, what you want is to clear the applications off of a node so that you can take it down for service. And that's that's like a special kind of Kubernetes thing that it tells the app to start shutting down, et cetera, et cetera. So, yeah.
So, really quick,
Mm-hmm.
for your networking pieces, how is that implemented? Or are you just using like TC to like dial up like packet loss and corruption stuff on the node?
Oh, the implementation details for the network bossiness.
Yeah.
I do not know. That is the magic inside
That's what
of
I
the
want.
product. Yeah. Well, it's open source, and it's implemented in Go, I think, and so it should be.
All right,
readily-
I'll get to theirs.
Cool. Yeah, thank you. You know, we're always looking for contributors, and so to Litmus Open EBS and to any other product that Maya Data is working on.
So it's really interesting dealing with like client server stuff, and you're doing IoT or mobile. Like all that stuff is going to be coming out under like shattered like 4G or like whatever.
Yeah.
So when you're setting up, so if you're catching stuff like that on the back end, it would be very good to be able to simulate those kind of terrible real world conditions into your kind of wider testing.
Yeah. Why don't I see if I can get some more information about the implementation details of the network?
Because like ages ago, when you like did this stuff, just like with EC2 or stuff, you would like build like a proxy to like shatter those connections like going through, right? To like simulate those terrible network connections, whether it's latency, inject latency, or drop packets or things like that. So to be able to do it right at the catching node might actually, like in a more automated way, would actually be like a very interesting kind of project thing for me to look at.
I'd love to put you in touch with the developers.
Okay.
I'll make sure you've got my card.
Cool.
Yeah, that's fine. Anyone else? Are we done? Ah, yes.
Is anyone using Litmus with managed Kubernetes solutions like EKS?
Oh, sure. Yeah, we do. We do some of our stuff in ESX, but like our CI/CD stuff runs in GKE, and we do Litmus on that. So, and Litmus is implemented as just straight Kubernetes code, and so it runs fine whether it's managed or whether it's a MinIO or a Minikube cluster or anything. One thing, if you tinker with OpenEBS, be careful of node taints, especially if you're messing around with a small cluster or a development cluster. Try it out on something that's a little bit roomier first, and especially if you're using CStore, it's memory hungry. It's an implementation of ZFS that runs at user land. It needs RAM, and so it's in the documentation what the limits should be, and so and you can tinker with them, but if you tinker with them too much, then it's not going to work well. But yeah. All right. I think it's beer o'clock at this point, right?
That's right. Thank you so much.